Okay, and the maths professor is on the air once more. Okay, so for those with a keen mathematics sense, you may notice that I'm starting with chapter 18 here. Meaning that we are likely skipping over 16 and 17. All right, I cannot stand this. All right. Chapter 18, Group Technology and Cellular Manufacturing. One of my favorite subjects. All right, so we're going to talk about part families, machine groups, cellular manufacturing, how we use group technology, and how we analyze cellular manufacturing. So we define group technology as a manufacturing philosophy in which similar parts are identified and grouped together to take advantage of their similarities in design and production. Similarities among parts permit them to be classified into part families, and into each part family, some rain must fall. Processing steps are similar. The improvement is typically achieved by organizing the production facilities into manufacturing cells that specialize in production of certain part families. You must forgive me if I slip out for the merest second to grab the book, since I was planning on doing a problem or two when we get to that point. All right. All right, so taking group technology from an overview standpoint, often parts in the medium production quantity range are made in batches. Disadvantages of batch production, they're listing as downtime for changeovers and high inventory carrying costs. Of course, in lean production, we discuss having single-minute exchange of die events to reduce changeover time so that we don't carry a high inventory. Group technology is supposed to minimize these disadvantages by recognizing that although the parts are different, there are groups of parts that have similarities. So, part families in cellular manufacturing, we use group technology to exploit the part similarities utilizing the similar processes and tooling to produce them. So our machines are grouped into cells, each cell specializing in the production of a part family. We call this cellular manufacturing. And we can have cellular manufacturing using either manual or automated methods. When it's automated, we often use the term flexible manufacturing system. All right, so when do we use group technology in cellular manufacturing? Our first instance is that the plant uses traditional batch production and a process type layout. Of course, the result of that is a lot of material handling effort and a high in-process inventory with long manufacturing lead times. We can group our parts into part families, which is necessary to apply group technology. And then every machine cell every machine cell is designed to produce a given part family or a limited collection of part families. So we have to group the parts into families. So what are the problems with implementing group technology? First of all, there's identifying the part families. Looking at all the parts made in a plant and grouping them into part families can be a very large task. The second problem is rearranging our production machines into our group technology cells. So that's going to be time-consuming and costly to rearrange our machines into shells. And of course, the machines will not be producing during the changeover. So a part family is a collection of parts possessing similarities in geometric shape and size, or in the processing steps used in their manufacture. So our parts may look nothing like each other, but still have similar processing steps that causes them to be put into the same cell. So our part families are a central feature of our group technology. There are always going to be differences amongst the parts in a family, but the similarities should be close enough so that the parts can be grouped together in the same family. All right, so here we see an illustration. We have two parts identical in shape and size, but different in manufacturing. Part A, we produce 1 million units a year with tolerances of plus or minus 0.010 inch out of 1015 CR steel, and they're nickel plated. B, we produce 100 a year with a tolerance of plus or minus 0.001 inch out of 1880 stainless steel. All right, so here we see an illustration of 10 parts. They're different in their size, in their shape, in their material, but are very similar in terms of the manufacturing used. All these parts are machined from cylindrical stock by turning, and some parts, as you notice, require drilling. And others require milling. All right, so in a traditional process layout, we have shipping and receiving, from which we have stock and parts that are going out to different machines to be turned into the parts that are needed. So we have turning machines, milling machines, drilling machines, grinding machines, and assembly, which is either machines or manual, I'm not sure. Turning this into a cellular layout based on our group technology and part families, we have receiving with our stock and our parts are separated into which of the cells it would go into to be finished into the part or component that it's going to be. All right, so how do we identify part families? Well, one way would be intuitive grouping. These parts look kind of alike, so we put them together. Or visual inspection, as it were. So in this case, we use our best judgment to group the parts into the appropriate families based on looking at the parts or looking at photos of the parts. All right, the second is a parts classification and coding scheme. In industry, this is quite common to have some kind of a code attached to every part. That part of the code tells you about its characteristics. So in that case, we're identifying those similarities and differences among the parts, and we're relating them by the coding scheme. And then the third is production flow analysis, where we use the information that is on the route sheets to classify the parts. So when we use parts classification and coding, our numerical coding system identifies the similarities among the parts and relates those similarities together. This is the most time-consuming method and has to be customized for any given company or possibly industry. Now, there are reasons that we might be using a coding scheme, such as being able to retrieve the design easily, to have automated process planning, and machine cell design. So we start with the idea we might be organizing into work cells when we use this scheme. So when we classify and code and create a system for that, it can be based on the design attributes of the part, the manufacturing attributes of the part, or both the design and manufacturing attributes. All right, so when we talk about the design and manufacturing attributes, the part design attributes could be the basic external shape, the basic internal shape, a rotational or rectangular shape, length to diameter ratio, aspect ratio, the material type, the part function, the major dimensions, the minor dimensions, tolerances, or surface finish. When we talk about the manufacturing attributes, that could be by the major processes, by the minor process operations, the operation sequence, the major dimension of the part, the surface finish, the machine tools used, the production cycle time, the batch size, the annual production, the fixtures required to make it, and or the cutting tools used in the manufacturing. Okay, so you can see there's quite a wide variety of how we might classify parts to put them in families. When we do production flow analysis, in that case, we're identifying part families and thus the associated machine groupings based on the production route sheets rather than on our part design. So work parts that have identical or similar route sheets get classified into part families. The advantage of using this is parts with very different geometries may still require the same or similar processing, while parts with nearly the same geometries may still require very different processing. So our steps in our production flow process, first of all, there's data collection. What is the operation sequence and the machine routing for each part? We're going to sort by those process routings, and if parts have the same sequences and routings, they're going to be arranged into packs. we're gonna take those packs, and each pack is gonna be displayed on a production flow analysis chart, which we also call a part machine incidence matrix. Then we're going to do cluster analysis so that we collect packs with similar routings into groups. Each machine group then becomes a machine cell. All right, so here's a production flow analysis chart, also known as a part machine incidence matrix. Have you already had facility design?
I think I have.
That's some good firmness of remembering there. If you haven't, it's going to be offered in the spring. All right, so here we see the parts go from A to I, and the machines go from 1 to 7. And where there's a 1, that means that part A goes to machine 1, and part A goes to machine 5. Part D only goes to machine 1. Part H goes to 1 and 5. Already sounds suspicious as hell to me. All right, so when we have that, well, here they have already rearranged that into possible machine groupings. So having machines 3, 2, and 6 together, and having machines 1 and 5 together, and having machines 7 and 4 together makes sense within the example. And we will do a problem or two on rank order clustering when we're done today. When we're done with the presentation, I mean. All right, so cellular manufacturing, we're applying group technology and taking dissimilar machines and processes and aggregating them into cells which are dedicated to production of a part family or a limited group of families. So typically our objectives with cellular manufacturing are shortening our manufacturing lead times, reducing our work in process, improving quality, simplifying production scheduling, and reducing setup times. All noble goals, I'm sure you would agree. So a composite part for a given part family is a hypothetical part that includes all of the design and manufacturing attributes of the family. Usually, an individual part has some of the features of the family, but not all of them. So, a production cell for our part family would be all the machines required to make our composite part. If we had a cell like this, we would be able to produce any family member and omit all the operations for features that aren't possessed by the composite part. All right, so the composite part, in this case, they're showing us the idea of a composite part for a family of machined rotational parts. All right, so the composite part would have a two turned sections. It would have a thickness, I'm not describing this correctly. It would have a cross section that would look something like this. So all the individual features of our composite part, part one, or the first part, is a turned, rotated part. And inside, it has a hole through it. Our second part of the composite part is that it has two turn sections, and the hole in the center has two different diameters for different parts of the hole. And then for the third part of the composite part, it has a sleeve inside one part of the hole. So, are you looking at that on the internet?
No, I'm checking my message.
All right, so theoretically, there are 7 different features for the composite part. So those 7 features would be the external cylinder, the cylinder face, the cylinder step, smooth surface, an axial hole, a counterbore, and internal threads. Right, so you'll notice that you've got 2 turning operations. You have a facing operation. A grinding operation, essentially 2 drilling operations, because drilling and counterboring are much the same, and a tapping operation. All right, so when we're talking about machine cells, you can have a single machine. We could have multiple machines that have manual handling. Usually we organize a cell into a U-shaped layout. We can have multiple machines that have semi-integrated handling. In other words, they're partly automatic in their loading and unloading characteristics. Could be an automated cell where it's automated processing and integrated handling. Often these are thought of as a flexible manufacturing cell or a flexible manufacturing system. All right, so here they illustrate a machine cell with manual handling. And we have work in, which is, there's a process that's manual here, a process that's manual here, a process that's manual here, process manual, and work out. What is wrong with this work cell? Don't worry, I'll wait. What's wrong with it is it's going the wrong direction. You should feed in and things should go from right to left. Here we have a cell where we have semi-integrated handling. So it's, in this case, it's an inline layout. It has mechanized work handling between the machines, right? But the workers must grab the product and do their process manually. Using a loop layout like this gives us variations in part routing between machines. Okay, so once again, it's we have mechanized work handling as far as the movement of the parts with manual processes. Using a rectangular layout gives us variations in the part routing again, and lets us return work carriers if they're used, although we could do that in the loop type layout as well. All right, so we have 4 different types of part moves in cellular manufacturing. We can have the number 1, repeat operation. Oops. The number 2, in sequence move. Number 3, a bypassing move. And 4, we could have a backtracking move. All right, we have the key machine concept, and that applies only to work cells where there's only one machine. And it's called the key machine, strangely enough. We usually have this when the machine is more expensive or is performing certain critical operations. We may have other machines in the cell that are supporting machines, but it's the most important to maintain high utilization of the key machine, even if that means lower utilization of the supporting machines. Okay, so easy enough. All right, so when we have these applications of group technology, one thing is we have different ways of forming our machine cells. One is we have informal scheduling and routing of similar parts through the machines that minimizes the number of settings. We can have virtual machine cells where we have dedication of certain machines to produce part families, but we don't actually physically relocate the machines. And we can have formal machine cells where we physically relocate the machines to form the work cells. We can also have automated process planning, modular fixtures that apply across a parts family, and parametric programming in our numerical control. All right, so what are the benefits of group technology when we're talking about manufacturing? Well, one is standardization of our tooling, fixtures, and setups, right? As much as possible, we want to make everything standardized. Second, our material handling is reduced. Our parts are moving within the machine cell rather than having to move through the entire factory. That means that our process planning and our production scheduling become much simplified, and our work in process and our manufacturing lead time are reduced. We also get improved worker satisfaction in a group technology cell and higher quality work. So when we do product design applications of group technology, we use design retrieval systems. First of all, for new part designs, we may do an industry survey to find out if existing part designs could be used. So that would be about 20% of the time. If an existing part design could be used with modifications, that's 40% of the time. Or a new part design is required, and that's 40% of the time. We always want to simplify and standardize our design parameters, such as the tolerancing, the chamfers, hole sizes, thread sizes. When we do that, we reduce our tooling and fastener requirements for manufacturing. All right, so when we do analysis of our cellular manufacturing, one of the things that we do is group parts and machines by rank order clustering. Usually this is in conjunction with production flow analysis. When we arrange the machines in a group technology cell, we usually use the Hollier method based on from-to charts. And there you have it. A super fast romp through the idea of group technology. And believe me, I know whereof I talk, since we once produced a 2-day training on work cells and group technology when I worked for Texas A&M. All right. They talk about rank order clustering without actually going through how we do rank order clustering. On page 521, example 18.1, they do an example of rank order clustering. All right. So I'm going to go through this idea super quick, and then we'll do some original problems. Well, they won't be that original. They're in the book already. All right, so we are initially given the machines are 1 through 7. Our parts are A, B, C, D, E, F, G, H, and I. All right. Then we see, for example, part A goes through machine 1 and machine 5. B goes through 4 and 7. C goes through 3 and 6. D only goes through 1, well, easy peasy. E goes through 1 and 2 and 3. F goes through 4 and 7. G only goes through 7. H goes through 1 and 5. And then I, it's a wild thing. It goes through 2, 3, and 6. All right, so what we do then is we score the parts based on what machines they're going through and how many they're going through. All right, so here this column gets a 1, which is 2 to the 0th power. This gets a 2, which is 2 to the 1st power. Maybe I better start putting parentheses. All right. Here, this is 4, which is 2 to the 2nd power, of course. Uh-oh. 4, which is 2 to the 2nd power. 8, which is 2 to the 3rd power. I think you're probably starting to get the idea how we're going here. Right, so this is 16, 32, 64, 128, and 256. All right, 256 is 2 to the 8. Oh. God damn it. 256. 2 to the 8th power. Right, and then you can see, all right, 128 is 2 to the 7th, on down. 2 to the 6th, 2 to the 5th, 2 to the 4th, etc. Now, I'm very sorry that I put all the 2 to the whatever power, right? Because right now we're going to do, what they're saying is you read all of these lines as though they're binary numbers, right? So you have, any place you have a 1, that's obvious, but any blanks are zeros. All right, so we would say this is equal to 256 plus 32 plus 2 then we look at our next one, we say it's equal to 16 plus 1. Our next line would be equal to 64 plus 16 plus 1. Our next line would be equal to 128 plus 8. Oh, that's all. All right. Our next one would be equal to 256 plus 2. Oh, well, that's it. Our next line would be equal to 64 plus 1. And finally, our line for machine 7 would be equal to 128 plus 8 plus 4. All right, so this is our ranking. Or they say decimal equivalent, but then what we're going to do is we're going to say, all right, we're going to take this, I'm going to copy it, here, and I'm going to look at it and go to my data tab and do a sort. All right, so my data has headers, it's already identified that. I'm going to sort by ranking, and I'm not going to go smallest to largest, I'm going to go largest to smallest. Right, so I rearrange so that it's now machine 1, 5, 7, 4, 3, 6, 2,
This one will take or the other?
rather than a straight 1 to 7 like it was before.
Just turn it on. Put it down there.
This one?
Yeah. Then,
Hey, don't let him be using my scanner over there.
okay, so it's on. You need to click this one or turn on.
Okay.
Look at the real time because it's idle a long time. And then it's in the flatbed, one side. Try to make sure that it's by 11. Okay? Because that's by 11.
All right, so that's what we did last time. Now,
We don't
to make it exciting,
just scan it.
we're going to
Oh, right. No paper.
there we go, clear contents. Now, we're going to go the other direction and go,
Okay, flatbed.
this is my 1,
This is flat.
2, 4,
It's, big paper.
8, 16, 32,
Black and white.
64, and, oh, that's all there is.
So after each one by one, let's go.
Okay, so then my addition becomes that I have 164 and 132.
No, it takes time because it's just just like heating up, right? Yeah, put this-
Here I have 116 and 1/8. Here I have 1/4 and 1/2.
Three. No, it's the third.
Here I have 164.
It's wrong time. You see that?
Here I have a 4 and a 1. Here I have a 16 and an 8.
I never did this.
Okay, well, there are 5 pages, right?
Here I have a 16.
What's the name?
Here I have a 64 and a 32. And here I have
No.
a 4 plus a 2 plus a 1.
Is it blocked already?
Now, I've also seen this done where we don't use a 1, we start with 2, then go 4, 8, 16, etc. Doesn't matter, it's going to work out either way. Except that,
And then all you're gonna do for money is,
No, it's not off.
now what we're going to do,
and then,
boy,
then paste here. Yeah. So it's here on the Kingston, then.
can we do sort sideways?
The you flash that from this.
And system of the.
This one?
That's it. You're good to go.
The contact. Very good.
All right, if I want to use the sort function, I'm going to have to do a copy transpose All right, so I'm still on sort. I'm going to sort again by rank, largest to smallest again. The convention is when we have two that are the same, like we have two 96s, two 24s, that we leave them in the same order. And my data has headers, all right. Now you'll notice that it seems as though it has sorted itself into 3 clusters, right? Parts A, H, and D are going to have a cluster of these 2 machines. B, F, and G are going to have a cluster of these 2 machines. And then I, C, and E will have a cluster of these 3 machines. All right, so let's do an example that hasn't already been worked out for us. All right, so,
Right. Sometime down.
machines. A, B, C, D, E, F, and these are the parts. And how many machines have we got? We got 1, 2, 3, 5, and 6. All right, so part A goes to machine 1 and 3. B goes to 3 and 5. C goes to 4 and 6. D goes to 2, 4, and 6. E goes to 1 and 5. And F goes to 2 and 6. All right, so using my scheme again of 1, 2, 4, 8, 16, and 32, right? We can rank these machines. All right, so A equals 32 plus 2. Machine 2 is 4 plus 1. Machine 3 equals 32 plus 16. Machine 4 equals 8 plus 4. Machine 5 equals 16 plus 2. And, uh-oh, there's been a rift within the lute, which growing larger makes the music mute. Equals 8 plus 4 plus 1. All right, so again, we can go to sort. My data has headers, yes it does, rank, but we want largest to smallest. It would actually end up the same if we used smallest to largest consistently. All right, so now we have these guys partially sorted. And if I take and copy pivoting at the same time so that I still have a rank here. All right, so my parts, oops, we're going to go by 1, 2, 4, 8, 16, and 32. All right. So we say this one equals 32 plus 16, yes, that's all. This one equals 32 plus 8. This one equals 4 plus 2. This one equals 4 plus 2 plus 1. This one equals 16 plus 8. And this one equals 4 plus 1. All right, so once again, I'm going to sort. My data does have headers. I'm still going to sort by rank. I'm going to sort from the largest to the smallest. All right, would you argue that that is sufficient clustering? Or are you still dissatisfied? You think we could go one more for the Gipper, as it were? Well, let's give it a shot. And see if we get any more clarity. All right, so once again, 1, 2, 4, 8, 16, 32. And of course, over here, we do rank. All right, so this equals 32 plus 16. This equals 32 plus 8. Oh. This equals 16 plus 8. This equals 4 plus 2 plus 1. This equals 4 plus 2. This equals 4 plus 1. Well, those are already ranked, so I'm saying, I'm going to call it that this is probably the best clustering we can do. That parts A, B, and E would go with machines 3, 1, and 5, and that parts D, C, and F would go with machines 6, 4, and 2. Okay, so what do you think? You're pretty excited by this idea? You could hardly care less, but you want to be polite. All right, anyway, that's rank order clustering. If you have a sufficiently complicated problem, you can end up doing 5, 6, 7 transformations before you get to the final clustering that looks like it works. Right, obviously, this isn't a very complicated. I'm not 100% happy with identifying parts by A, B, C, etc., and machines by 1, 2, 3, etc. But, there you have it.
In industry, how would you label those? Would it be by machine, name, part name?
A lot of times we would have part names. Usually, everything ends up having a name, even if it's an informal thing, right? So the part names might be like 101, 104, 107, etc. And the machines might end up with kind of informal names, even though they may have a formal name and an informal name. Right, they might be known by the people who run the machine, you know, so you got Joe's machine, Frank's machine. Right, depending on how large a facility, right, it might just be, oh, the new CNC machine, the old lathe, you know. But if we start talking like a factory where we are producing a lot of stuff, you want to put in a more formal system. Tell you what, we've still got a few minutes. I'll get you on started on a problem that I'll then assign as homework. So 18.4, yeah, that's a ticket. All right, so. Machines. All right, and what do we got for that? We got A, B, C, D, E, F, G, H, I. And on machine 1, we run C, D, and E. On machine 2, we run A, B, G, and H. On machine 3, all the way over to F, G, and H, on machine 4, A, B, D, and on machine 5, we run C, E, and H. On machine 6, we run B, H, and I. Oh, man, I thought I was gonna get left out. Oh. G, H, there should be a 1 there as well. All right. 7, runs A, C, D, and that's all. And 8 runs B, F, H, and I. Oh. All right, so once again, we go 1, 2, 4, 8, 16, 32, 64, 128, and 256. Boy, they. All right, and finally we have to figure out rank. All right, so for machine 1, it's a 64 plus a 32 plus a 16. That's it for that. For machine 2, it's a 256 plus a 128 plus a 4 plus a 2 plus a 1. For machine number 3, it's an 8 and a 4. For machine number 4, it's a 256 plus a 128 plus a 32. And for machine number 5, it's a 64 plus a 16 plus a 2. For machine number 6, it's a 128 plus a 2 plus a 1. For machine 7, it's a 256 plus a 64 plus a 32. And finally, bringing it home, machine number 8 is a 128 plus an 8 plus a 2 plus a 1. All right, so I apply the sorting paradigm again, largest to smallest. Copy and there we go. And of course, once again, it would be the 1, the 2, the 4, 8, 16, 32, 128, and 256. You notice all their matrices are the same size, going both ways. I don't know, I thought it was interesting, obviously it's not. Okay, the rest is left as an exercise for the students, as the old teaching saying goes. Okay, so are there any questions? Okay, well, according to the computer clock, we're at exactly time to stop. And we will look at the other methods of dealing with group technology on Wednesday's class. All right, well, thank you very much. I hope you had fun. Or at least are feeling like you're still alive. Oh yeah, save this in Cpt Aided Manufacturing. And these are chapter 18 examples. All right, that's it for class today. I will see you on Wednesday. And I will remember this time to turn off the phone so that I don't suddenly have students questioning me when I'm walking and singing.